Hi, and welcome to part 9 in creating a DLX architecture simulator. In this video, we're going to start implementing the remainder of the base instructions that can be found in the spreadsheet that will be in the description of this video. We're going to start by implementing the R-type instructions that we haven't already implemented in the previous videos, and then we'll move into the I-type instructions we haven't already implemented, and then do the last few with the J-type, which is just jumping. And then at that point, we will have our single cycle data path machine good to go and ready to use. And we can actually write some real assembly that we will be able to execute. So to start, what we'll do is we'll open up our R-type instructions header file, and we'll start adding in function declarations for all of our R-type instructions. So we're going to have just copying out what we have for add and subtract for all of the different ones that we have to implement. So we have shift logical left, or shift left logical, shift right logical, and then we'll have shift right arithmetic, and we'll have add and subtract, which we already have. We'll have and. We'll have or. And we'll have XOR or exclusive OR. Now let's actually just copy this out. And then we'll have 1, 2, 2, 3, 4. And with these, they're going to have set if equal, set not equal, set less than, and set less than or equal. So those are our R-type instructions. So now, everything except add and sub will copy out. We'll go to the C file. We'll remove this breakpoint, and we'll paste in the declarations, and then we'll just fill them out. So we're going to have data and reg info, and then so shift logical left is rd equals rs1 rs2 mod 8. Mod 8. So we will need to get rs1 will be rs1 mask, rs1 offset. And then rs2, get that from the register info. And then what we'll do is we will return we're going to return our return registers GPR rs1. Put this in brackets. Left shift bracket registers GPR rs2 mod 8. Oh, put a semicolon at the end. So that's that. That's shift left logical. So now we'll do the next one. Shift right logical. We'll have data, and we'll have reg info. And this one is rd equals rs1 shift right rs2 mod 8. So we'll get rs1 the second register. And then we'll return basically the exact same thing as above, except instead of shifting left, we're going to shift right. And we'll put another bracket here, mod 8. And then shift right arithmetic is the exact same thing as shift right logical. So I don't know why it's even implemented a second time, but what we'll do is we will just have this be a call to shift right logical, and we'll just return the value that's returned. So that was pretty easy. So now the last ones here, we'll implement them. Put all the brackets in right away. Alright, so we'll take and we'll get the first, this is going to be RD equals RS1 and RS2. So we'll need RS1 and then we'll call RS2. Actually, what if we were to make this a function call? So let's go hword extract register, and we take in the mask. Actually, this is hword mask, hword offset, hword register info, and then we just go return reg info and mask right shift offset, and then we can just call hword rs1 equals extract register. Oh, we spell register right. Put an E in, and then we want rs1 mask, rs1 offset, and reg info. And then we can go extract register, rs2 mask, rs2 offset, and reg info. Do the same thing for all of these. So we can actually just duplicate this now. So paste that in all of these. And these errors will go away once we have actual definitions here. Reg info. So let's copy this as well. Paste it in all of these. And then now we can just perform the operations here. So and we want register registers GPR, and we want rs1 and registers GPR rs2. And in this one, it is rd equals rs1 or rs2, So return registers GPR rs1 or registers GPR rs2. And then XOR is RD equals rs1 XOR exclusive OR rs2. So we'll return registers GPR rs1 exclusive OR registers GPR rs2. And then set equal then, or set equal RD equals rs1 equal to rs2 1 0. So it's basically an if statement. So if rs1 is equal to rs2, we want to set rd to 1. If it's not, set rd to 0. So we return. Actually, let's do this as an if statement so it's easier to understand. So if registers GPR rs1 equals registers GPR rs2, return 1, else return 0. So you can write this in a conditional exactly as it is here, but just for simplicity's sake, I've written it out as a full if statement. So set not equal is rd equals rs1 not equal to rs2, 1 if it's true, 0 if it's not. So again, if registers GPR rs1 equals registers GPR rs2, then we want to return 0. So you can actually remove that. And then else return 1. And then we have set less than. So this is rd equals rs1 less than rs2 1 0. So we have if registers GPR rs1 is less than registers GPR rs2, return 1, else return 0. So with this, we don't have greater than, so this is something we could add on as an expansion. But for right now, we're just going to implement the bare minimum, and then after that, we can implement whatever else we want to implement that's not already implemented. So here we have rs1 is less than or equal to rs2 1 0. So we have if registers GPR rs1 is less than or equal to registers GPR rs2, return 1, else return 0. So those are all of our R instructions. Now we can close this and close this and go to the instruction handler, and we can implement these where they would go. So 4 is shift left logical, so 0 1 2 3 4. So we can highlight this and go SLL instruction. And then we should actually change these so that they match. So get memory address. We're going to go to our itype. Oh, that's why we don't have the actual load word and start word. Okay, so we'll leave those. So next is shift right logical, which is 6. So we have SRL instruction, and then we have shift right arithmetic, which is 7. SRA instruction, and then we have AND, which is 36. So 2 after sub. So we have sub should be 34. So for some reason our subtract is in the wrong position. 28 is actually SLEI. So this should be nope. And then this is 32, which is right. 34 is sub. 35 is load word. Okay. So then 36 is and. So all the way at the other end here. So and instruction. And then or is 37. And then exclusive or is 38. 40 is set equal that, or set equal, SEQ instruction. 41 is set not equal. 42 is set less than. And 44 is set less than or equal to. So now all of our instructions are in, our type instructions are in there. So now we can go to iType, which has a significant amount more, and implement those. So let's go to iType H and implement these. So we have word BEQZ instruction, word H word, which is branch if equal to 0. We have word BNEZ instruction, which is branch not equal to 0. We have add I instruction, which is add immediate. We have subtract immediate. We have and immediate. We have or immediate. We have exclusive or immediate. So this is definitely the least interesting part of all of this. We have load high bits. We have jump register. So that's JR instruction. We have jump and link register instruction. We have shift left logical immediate instruction. So one of these instructions are instructions we've already implemented. It's just instead of using a register value, we're using an immediate value. So we have SRLI instruction, shift right logical immediate. We have shift if equal immediate, or set if equal immediate. We have set not equal immediate. We have set not, or set less than immediate. We have set less than equal to immediate. And then that's all for I. So now let's copy all of these. Let's go into our itype.c and let's paste all these in. Let's see if we can do a can we do a find and replace? Let's replace it with can we do that? No, that just... Does that work now? It does. Okay, so let's do that. So let's go new line, bracket, new line, bracket, new line. Makes it a little bit easier. Perfect. All right. Now, let's copy that. Control F, paste that, and let's replace it with word data hword reg info. Perfect. Much easier. All right. So branch if equal to 0. So we want PC plus equals rs1 equals 0. Extend immediate 0. So let's write, actually this is different. This one we can't do the same way we do the other one. So let's go word. Actually, we can set this to an hword. I think the other one could be an hword too. Let's check to make sure. Immediate value is 16 bits. Yes. Alright, so let's go back here. Let's change this to an hword as well. There's no reason to get really large, use unnecessarily large values. So hword rs1 equals reg info and rs1 mask shift 10. Actually, let's make that a define rs1 offset. Just make everything not hard-coded. So we have the register value. So now we need to check if rs1 registers GPR rs1 equals 0. Then we want to return well, we need a way to say that it's going to be the program counter. Well, let's just return it for now. And we'll return immediate. So we'll need to return data and immediate mask. And else return 0. So now branch not equal to 0 is PC plus equals rs1 not equals 0. Extend immediate 0. So hword rs1 equals reg info and rs1 mask rs1 offset, and then if registers GPR rs1 does not equal 0, return data and immediate mask, else return 0. So now we'll need add I. So that's right. Actually, no, let's copy these, because we'll probably need these in all of them. So we'll paste it in all of them again. So now we have our register 1 and our immediate value in all of these. So now we want to return So this is going to be rd equals rs1 plus extend immediate. And like I said last time, the values are automatically extended since we're doing this in C, so we don't have to actually do an extend. So we can just set the value. So we can return rs registers GPR rs1 plus immediate. Which is exactly the same as the get memory address. Ha! There we go. So this is going to be rd equals rs1 minus extend immediate. So again, we can just return registers GPR rs1 minus immediate. And this is going to be return rs1 and extend. Oh, this is just immediate. So it's the exact same thing. So we can return registers GPR rs1 and immediate. This is going to be rd equals rs1 or immediate. So we return registers GPR rs1 or immediate. So this is going to return rs1 exclusive or immediate. Return registers GPR rs1 exclusive or immediate. So now we get into a little bit more complex one. We have load high bits. Actually, it's not even that complex. We say rd equals immediate shift 16. So we don't even need rs1 in this one. We just return immediate or im shift 16. Jump register is going to be pc equals rs1. So here we just return rs1, or registers GPR rs1. And jump and link register is pc equals, or r31 equals pc plus 4 pc equals rs1. So we want to return registers GPR rs1. And then shift left logical immediate is rd equals rs1 shift immediate and or mod 8. So we return registers GPR rs1 im mod 8. And then shift right logical is the exact same thing as above, but instead of shifting left, we shift right. So immediate mod 8, and we return registers GPR rs1 im mod 8. So now we have set equal immediate, so rd equals rs. Oh, we forgot shift right arithmetic. So let's go add that one. Word shift right arithmetic into immediate instruction word hword, which is just like the other shift right arithmetic. It's going to be just a call to so it's going to be return srli instruction, and we need data reg info. So it's just going to return the shift right logical since it's implemented as shift right logical. And then this one's going to be rs1 equals extend immediate, and 1 or 0. So if registers GPR rs1 equals immediate, return 1, semicolon, else return 0. And then we have rd equals rs1 not equal to extend immediate 1 or 0. So if registers GPR rs1 not equal to immediate, return 1, else return 0. And then we have set less than or set less than equal to. So equals rs1 less than extend immediate, and then 1 or 0. So if registers GPR rs1 is less than immediate, return 1, else return 0. And then here we have same thing as above, but less than or equal to. So if registers GPR rs1 is less than or equal to immediate, return 1, else return 0. So there we are. That's all of our I-type instructions. And then finally, our two J-type instructions. So we have word, jump, that's word, H word, and then word, JAL instruction. And we'll add all of these to the instruction header at the same time. So we'll do that in a second here. So we need to include JType instruction.h, word, J instruction, word data, H word reg info, and then word JAL instruction, word data, H word reg info. So J instruction is PC plus equals extend value. So value is going to be the parameter passed in. So it's a 26-bit value. And if we go to state handler.c, I believe data is the entire instruction, or decode data is instruction and data mask, which is everything except for the first 6 bits. Okay, so we do have all that. So we basically need to say return data, and then JAL is R31 equals PC plus 4, PC plus equals extend value. So again, we return data. No big deal. Those are simple enough. So now if we go to instruction handler and we go through this, so we start at 4, 0, 1, 2, 3, 4. Oh, we have 2 4s. That cannot be right. Let's see which one is right. I need to find one with the numbers. The opcodes. Yes, okay, so let's see. We have, so BEQZ is 4, and so is shift left logical. Interesting. So this is where that zeroed out opcode comes in. So if we remove get memory address, that's our only I type right now. So NOP instruction and NOP instruction. So there we are. So these are our R-type instructions. So these are all of our R-type instructions now, and we'll create another one that is I and J. Actually, let's go static instruction func IJ type instructions equals. All right. So because we can have two 4s, because if it's a 0 and then a 4, it goes to R-type. If it's a 0, if it's not a 0 at the beginning, then it goes to IJ. So it's kind of a little bit interesting, but it says we have this unformatted, or this. So it's this. The opcode for R-type is 0, and then the function code is SLL. So I should actually put that in the DLX sim. So we have opcode always 0, and then function code. That's probably a little bit more clearer. So now in here we can have NOP instruction. So that's 0, 1, 2, 3, and then 4 is going to be BEQZ instruction. 5 is going to be BENZ instruction. 6 will be a no-op. 7 will be a no-op. 8 is going to be add I. 9 is going to be a no-op. 10 is going to be sub I. 11 is a no-op. So what do we have? We have 6 and then 6. So then 12 is going to be and I. 13 is going to be or I. 14 is going to be exclusive or I. 15 is load high bits. 16 is a no-op. 17 is a no-op. 18 is JR. 19 is JALR, jump and link. 20 is shift left logical. 21 is a no-op. 22 is shift right logical. 23 is shift right arithmetic. 24 is set if equal to. 25 is set not equal to. 26 is set less than. 27 is a no-op. 28 is set less than equal to. 29 is a no-op. 30 is a no-op. 31 is a no-op. 32 is a no-op. 33 is a no-op. 34 is a no-op. 35 is load word, which is get memory address. Load word. And then 36 is a no-op. 37 is a no-op. 38 is a no-op. 39 is a no-op. 40 is a no-op. 41, 42, and then 43 is get memory address again as store word. And then we have jump, which is 2. So J instruction, and then 3 is jump and link. So there we are. That's all of our instructions in this now. So now we need to go to our state machine, our state handler, and we need to handle those very few edge cases where we're setting the program counter and not the register, and also we need to select if it's R or I type. So to start, we can go well, we'll need to have a way to determine if it's R type or I type. So what we need to do is we need to actually what we can do is we can check if the opcode mask shifted by 26 is equal to 0. So if instruction s instruction and opcode mask, let's put another bracket here, shift opcode offset equals 0, then we want to get it from R type instructions. Otherwise, we want to get it from IJ type instructions, response and opcode info mask shift 16. Alright, so now we got that. So now for the operations where we set the program counter or a specific register like register 31. So let's find all those instructions. So there is 6 of them. So we'll want to do that in the write back stage. So we'll go down to write back, and let's pass in the opcode to write back as well. Actually, we don't store the opcode. So let's do, well, what else are we doing here? We have, okay, just the write value. So we set the write value if it's an I type and if it's a J type. So let's remove this for now. So we have let's see, what can we do? We have, let's put that back in. So this is going to be if it's greater than 2, 3. So if it's greater than 4, if it's 4 or higher, it's going to be a 1. Or if it's not store word opcode, then it's going to be a 0. So for JAL, which isn't true because JAL we want to set register 31 to PC plus 4. So there really is never a case where we actually don't return a value, because store word is actually let's do if. So if opcode does not equal SW opcode, then, because SW we don't want to actually store anything, because we have a value in RD, and it's weird, so we'll do that. And then what we'll do is, we'll pass in instruction. We'll go up to write back. Write back already only has one word. Is that write back we were in? Write back needs two. So I don't know why it has only one up there. So let's add word. So now we have instruction. It's actually an H word, not another word, so let's do H. Oh, one H. Okay. So now we can say if instruction and opcode mask 26. We should actually use opcode offset and opcode offset, because I believe that's what 26 is. Yeah. Okay, so we go opcode offset. Let's actually go there. So if that equals, so we can say 4, 5, 2, or 3. So if it's less than 5, is less than equal to 5, or actually let's get H word opcode equals instruction and opcode mask shift opcode offset. So now we can go if opcode is less than or equal to 5, or opcode equals 18, or opcode equals 19. I should just handle these all separately. So if it's less than or equal to 5, this is BNEZ, BEQZ, J and JAL. So we want program counter. So let's move the program counter into the registers. So we have dword program counter. So let's go to register file handler.c, and in create registers, actually let's go to state machine.c. We have create registers. So let's go let's go registers program counter equals 0. Okay, and then we can go registers program counter equals, and then registers program counter. So now let's go to state machine.h and remove program counter. And that should tell us if there's any problems with referencing it. But now we can go to register handler.c, and we can say, okay, registers. So registers program counter equals value. Yes, and before we do that, we actually want to go if opcode equals 3, then we want registers GPR 31 equals registers program counter. Oh, it's plus equals value, not equals value. And then, oh, this is actually plus 1. And the reason it's, so in the spreadsheet it says plus 4, but the reason we're doing plus 1 is because our memory is all by 4 bytes, not by 1 byte. So the plus 4 is for 4 bytes, so it means to the next instruction. But since our memory is all 1 byte, next instruction is just a 1. So that's why we do it that way, not the way they do it. So now we need else if opcode equals 18, and this is going to be JR. We want registers program counter equals registers. So actually, if you go to JR, which is an I type, we should be returning register 1. Convert these all to Unix. Not sure why it was that way, why it asked me, but anyway, so we have JR, which is jump register. So JR returns the value in register 1. Okay, so we can just say equals value. And then else if opcode equals 19. We want registers GPR 31 equals registers program counter plus 1, and then program, actually we can go is greater than or equal to 18, or opcode is less than or equal to 9. Greater than or equal to 18, and opcode is less than or equal to 19. Actually, we can just go equals 18, or opcode equals 19. Actually, what if we go switch opcode and then case 1, case 2. So if it's 1, we do and let's write a couple of functions. Let's go set. Actually, no, it's fine. Let's just scroll down here. So if it's a case 1, then we want to if reg info and return flag. Actually, yeah, let's write a function. Let's call it save value, and we'll pass in value and reg info. And RD. So we need a word, an H word, and an H word. So we have void save value, word, H word, H word. Let's scroll down. and go to void save value, word value, hword reg info, hword dest. So we have, and then break. Actually, let's go case 1. But let's go default. Default is save value, and we want value reg info and rd, and then we'll say if reg info and return flag hw equals return flag hw registers gpr rd rdest equals value. So now we can remove this, and then we can say, so this is only for if we have, so basically every single one goes in here that isn't going to be our special ones. So case 4, case 5, case 2, case 3, case 18, case 19. So in 2, we want PC to equal value. So registers program counter plus equals value. In 3, we want registers. So let's put a break in here. Break. Registers GPR31 equals registers program counter plus 1, and registers program counter equals value. And then break. On 4, we want, actually 4 and 5, we want registers, or no, registers program counter to equal value. Actually, let's put 3 above 2. The reason we're going to do that is because then we can actually remove that, and all of these can fall through. So we have 3. So if it's a 3, it'll set 31 to equal program counter plus 1, and then it will fall through to 5. Assign program counter to or program counter gets this value, and then it breaks. And then in here, we'll have 19. And this is the nice thing about switch case statements. You can reorder them to kind of do whatever you want. So yeah, if we get 3, it'll go and complete this operation. So set register 31 to the value of program counter plus 1. It'll go fall through to 2 and say, okay, nothing there. Fall through to 4, nothing there. Fall through to 5. Perform program counter equals value, and then break. And then here we have 19 first, because we can go again, registers GPR 31 equals registers program counter plus 1, and then we can fall through and go registers program counter plus equals value, and then should be plus equals as well. So that's just our way of cleaning this up a little bit. So then we can add other ones. So if we want to now say, oh yeah, instruction number 33, which doesn't exist, but we could write an instruction 33 and say, okay, case 33, it's also going to set program counter to the value. And it'll just fall through until it hits a break. So I'll put our breaks in here. And I'll put a break in here. So it'll fall through until it hits a break and then go out. So if it's not one of these, then it goes to save value and tries saving the value. So we now have all of our instructions implemented. So now what we should be able to do is go to filehandler.c, and we should be able to write any kind of instruction that we want to put in there, and it'll all work. So just to make sure we didn't break anything, we'll run a quick test again. We'll insert a breakpoint here so we can step through and make sure that our values are being set like we want them to be. Oh, there was build errors. That's not good. Unresolved external symbol state machine, or create memory. Let's clean. Oh, now why is it saying that? Let's go to initialize state machine. So there's no create memory. So let's go to memory.h, memory handler, memory create memory. Let's go to memory handler.c, create memory. Yeah, it's all there. Now why is it giving me errors? That's the real question. Let's try this again. Let's make sure it's included properly then. So memory handler, state machine.c includes state machine.h, state machine.h includes memory handler. What's the header guard in our memory handler? That's not a problem. No, that should be good. I'm not sure why it's giving me a problem. Error list. Execute. Has 3, 3. Oh, it needs another one. So let's go put instruction func word and h word. Let's attach the h word. So it's actually a problem with linkers. Let's go see what the linker says. See what it says for an error. These are all C files. There's a whole bunch of things that could possibly cause this. Doesn't say. Doesn't give me an idea of what's going on. So state machine.c, create memory. create memory. Because this was working before. That's just the exact same thing. Unresolved externals. Maybe that's the catch. Let's see what this one gives for an error information. It just tells you to look at the other information. What could this be? Memory, create memory. That's fine. Now why is it giving an error with the linker? Object specified. That's interesting. Object specified more than once. Can I view the intermediate files? Let's see. Let's go to memory handler. Let's compile this one. Okay, so there we go. Memory handler.obj object specified more than once. Well, why is it being specified more than once? Let's take a look. So state machine dot h memory handler state handler. Let's see if removing memory handler helps. Alright, let's see if that works now. Okay, so it's just one of those weird sometimes errors where the linker is just executing in a little bit of a different way. It's compiling it a little bit differently. Script. Sure. I guess so. Alright, so let's... Sure. That's where we were before. That's what we had last time, so let's skip. So, let's see, we would be... Oh, what's it? Show next statement. Okay, so we would be on execute right now. So if we skip ahead, so we've set the memory location, and that is right back. So now we'd be on the next instruction. So fetch, decode, execute, load memory, and the next one is right back. So boom, it still works. So everything is still working. It's all good. But at this point, we can write out larger assembly files and actually execute them now. So that's going to be it for this video. Um, and that's going to be it for the first part of our simulator. At this point, we have a fully working single cycle data path machine. We can write our assembly assembly file in as binary by doing a very crude way of doing it by doing this, and then writing out each individual instruction in binary. But the next section will be a little subsection where we create interpreter. We may not do it in C, we may do it in another language, but we'll see how it goes. And then from there we'll write an interpreter, which will read all of the assembly code and convert it into binary for us. And then we'll load that binary file into this program, which will convert it to put it into memory for us. We don't have to. And then from there we will be able to execute it without having to type out these stupid things like this. So until next time, happy programming.